Right, so next up is Benjamin from Dropbox, and he'll talk about test selection.
Greetings, salutations, hi. It's great to see all of you here this afternoon. I'm happy to be here. It seems like we find ourselves back in Sunnyvale. Sunnyvale, of course, is America's corporate campus capital, with representatives from all of the nation's most ethically tainted industries. But despite the sense of anomie and white-collar alienation pervading the place, this venue is quite an upgrade for BazelCon. Maybe it's a reflection of our rising status as a community. Maybe once you do 1.0, you get to use the grown-up conference center. But I will say that if this is your first BazelCon, you missed the experience of attending a conference held in a shoebox. I know a whole lot less this year about how my fellow Bazel enthusiasts smell. I hide Benjamin. My name is Benjamin. And I put food on the table these days by working for a company called Dropbox. Specifically, I work on Dropbox's development infrastructure team. And we're responsible for all the tools, continuous integration, build stuff that Dropbox engineers use to get their job done. And we've been using Bazel for quite a while now, about 4 years since it was originally became open source. I would say that we'd been using it before it was cool, except I think that still today build systems occupy a level of glamour and cultural cachet that is somewhere between like dentures and latex gloves. So I won't make that claim. But anyway, we've had over the years the opportunity to accumulate a lot of successes and titanic failures building tooling around Bazel. And we've talked about it the last two BazelCons. So we talked about generating build files. We talked about integration testing with Bazel. So go look up those if you want to hear about those topics. And we also, just yesterday, we released a bunch of our Bazel-related tooling on GitHub. So the URL is right there. You can go and find it. So this is our build file generator, our integration testing framework, and also our Python rules. So we can probably do something for your Python problems if you are willing to do things our way. But that's not really the topic of this talk. We also put up a blog post today on our tech blog about how we integrate Bazel in our CI system. It has a long URL, which I didn't bother to put up there, but if you go, I'm sure you'll be able to find it if you stick Dropbox Tech Blob in DuckDuckGo. I mean Google. All right, so we like Bazel because of its scalability, its focus on hermeticity and reproducibility, and because it tastes great on pasta and pizza. But I have a more personal reason for really liking Bazel, and that is that it contains my favorite Java method definition ever. Right. So verbosity is the standard in Java naming, of course, right? But in this case, the verbosity kind of obfuscates more than enlightens. And so there's 10 words in this method name. 5 of them are unique. The word 2 appears 4 times. And after thinking a long time, doing a lot of nail biting, consulting with top linguistics experts, I've come to the conclusion that the way you should segment this method name is convert library to link list to library to link list. Now, that's still a little confusing, right? Because if you ignore the fact that the argument to this function is a set rather than a list, it still seems like this function should not be doing anything, right? But everything becomes clear if you notice that there's actually 2 classes called library to link, right? There's the library to link package level class and the nested class of linker inputs. All right, so this brings a smile to my face every time I do a build, and you can think about what's inside next time you're running a build too. And I could probably give a whole talk about the hidden gems of Bazel, but unfortunately that is not this talk. and we were best getting back to the actual topic of this talk. To do that, I'd like to introduce kind of the framing story, an overall problem for this talk. There's a lot of problems in this talk, as you'll see. And that is what I'm going to call the selection problem. And here are the contours of that problem. So I run a continuous integration system, and Dropbox has millions of lines of code and thousands of primates making changes to this code. Sometimes they even write tests. And so the continuous integration system is exposed to these proposed changes in several forms. So pre-review testing, tests on code reviews, pre-submit tests, and tests after a change has actually landed. And every time the CI system sees a test, it has to decide what test to run. And in particular, we want to run the tests which are most useful for engineers to be seeing the results for a particular change. And one kind of logically obvious thing is that we should only run tests that can possibly be affected by a change. And so kind of in Bazel terminology, that means we should only be running tests that have a transitive dependency on files that were modified in a particular change. So this talk is going to be focusing on testing, but this idea of selecting targets, computing the targets which are affected by a particular change, has other uses too. For example, you can do things like only deploy binaries which have actually changed over a series of commits, and generate custom change logs from an overall change log for just the changes that affected a particular target. All right, so if we first see this problem, we might think, well, what's the problem? Why don't we just do this? Run Bazel test over our entire workspace. And as we've seen several times before in this conference, and as you probably know as a Bazel user, Bazel will not run the tests which it doesn't think need to be run, and sort of like print cached in the test results if it didn't run them. And so this solution has the advantage that it looks pretty simple on the surface. We don't have to build anything extra. And since we're using Bazel's built-in invalidation and caching logic, should be about as correct as Bazel, which is generally a pretty high standard. But on the other hand, this solution, Bazel test / has some serious scalability concerns. For example, we almost certainly are going to need to have remote execution for this to continue to scale, because large changes or changes to particularly common dependencies will trigger a lot of tests which won't be reasonable to run in a reasonable amount of time on one machine. This also still continues to do a lot of work kind of up to actually executing the actions in Bazel. So this does analysis, computes the command lines for everything, and that itself can take a lot of memory and a lot of CPU. So on a workspace of sufficient size, this is not really a reasonable thing to be doing. And then finally, this doesn't really give us everything we want. So it's a little inflexible. We might want to be able to apply custom policies to the kinds of tests we're running in our repository. For example, maybe there are some really expensive tests that we only want to run every a few hours or every day or something. But Bazel doesn't really give us the controls to do things like that just using Bazel test. And finally, we don't actually manage to produce an affected set of targets from doing this. Bazel just kind of executes what it thinks it needs to be executed and doesn't tell us what the true affected set was. So we need to do a little better, but first let's define our problem a little more closely. So the input to the selection problem is a set of change source files. So we can also think of this as being two revisions of a version control system where we're looking at the changes between those two revisions. These are equivalent ways of thinking about this particular input, and we'll be switching between them because sometimes it's convenient to think of it in one form or another. And then we also have a universe of targets that we're going to be searching for the affected targets within. So in this talk, in our examples, we'll always be using the entire workspace // but there's certainly use cases for a more restricted scope. Okay, and so our algorithm, our solution to the selection problem, is supposed to produce a subset of the universe that is possibly affected by those changes. So we're always going to have to be a little conservative. We can't always prove that a test is definitely affected by a particular change, but we want to be conservatively include all the tests that might be affected. All right, let me also show you the controlling example for my change here. All right, so we're going to be considering a little package called //foo. And here's the build file for //foo. All right, so I have a library, C++ library with a single source, lib.cc. And then there's a test called myTest, which depends on the library. And you'll also see at the top, there is a dependency on a starlark file called myrule.bzl. So this is kind of a very silly dependency. The whole thing is a bit contrived. But it'll work for our example purposes. And if you want to see a non-trivial build file, we're hiring. All right, so with the example in hand, we can start to think about how we're actually going to pick out the targets that are affected by a change. And this means we're going to be looking at the Basel dependency graph. And the tool to do that, of course, is Basel query. So Basel query lets us do post-loading inspection of the dependency graph. So that's a little bit of Basel jargon, loading. That essentially means that the build files have been executed from top to bottom, but rules haven't been instantiated. So targets are basically a name with a bunch of attributes attached to them, like sources and depths and so forth. And Basel query lets us manipulate this graph. It's a very extensive tool with extensive documentation. There's a good reference. You can also see the Basel query how-to document, which has a lot of neat examples about things you can do with Basel query. But like any sufficiently powerful tool, it has some complexities and gotchas which can cop up if you're trying to do some serious production things with Basel query. So for example, that I'm aware of 3 different internal implementations of query. 2 of them are even documented. And this is the kind of thing that's going to come up when you're doing like large performance-sensitive queries. So if there's one sub-theme of this talk is that you should treat Basel query with a little reverence and maybe a little fear. So anyway, if we go and look at the Basel query reference documentation, we'll quickly find some functions which will probably be helpful to us in figuring out what targets are affected given a set of changed files. So the first is the test function. So the test function takes a bunch of targets and it throws out all the targets that aren't tests. So we'll use this as a kind of final filtering phase in our algorithm to only pick out the test targets because that's what we're interested in running. And then the real workhorse is going to be the rdepth function. So the rdepth function computes the worst dependencies of a set of targets within a particular universe. So with these 2, it doesn't take much imagination to see that we probably want to do something like this. Okay, so we feed the change files into the rdepth function. We want to compute it over the entire universe. So that gives us all the rdepths transitively of those change files. And then we pick out the test. So if we run this on our really silly foo example, we'll see that indeed, if we suppose that our mylibcc source file was changed, then we'll see that we should be running foo //foo myTest. Great, right? Are we done? Well, if we were done, this would have been a lightning talk. There's a few problems, and many of them center around asking the question like, well, what if we mutate the build graph instead of source files? So here's the first of 3 problems. What if we modify a build file? Okay, so if we put a build file into our rdepth expression here, Basel will just say, nope, nothing depends on that. And to some degree, that's true, right? myTest does not actually depend on the build file to execute. But modifying the build file could certainly affect the test. So we're going to need something to deal with build files. But happily, if we go back to the Basel query reference documentation, we can find out some more functions which might help us with that. So specifically the siblings function. So the siblings function takes in a target and it returns all the targets which are in the same package as the input target. So this function is useful for computing all of the targets in a build file. And then we also have the filter function, which filters targets by applying a regular expression to their name. So with this, we can, given our set of changed files, we can filter out all the build files, and then we can compute all the targets that are in those build files. So there's this little subtle question, which is like, what targets do we actually need to mark affected if a build file is modified, right? So if all we know is the build file is modified, arbitrary things could have happened to the targets within it. So we basically have to run all the targets in that build file and all the targets which have a transitive risk dependency on that build file. But using these tools, we can kind of integrate our original RDEPS query and this fix for the build file thing. So I'm making use of Bazel query syntax to let you define a variable to store my changed files. And then I have the RDEPS over the changed files, and then also all of the targets in build files that were modified. And then again, prints foo test if changed files is /build. All right, so that fixes that problem. But we had 3 problems, so let's look at problem number 2. So another way you can modify the build graph is by changing a starlark file. All right, and if we tried the original RDEPS query, the result is even more horrific than the build file case. Bazel is going to tell us, I've never heard of this myrule.bzl file. What are you talking about? And it's also going to give us some hint about maybe you want to put export files in your build file. So we can go and put export files in our build file, but that's really not going to help us very much and kind of just stick us back at the situation, the build file. It's a red herring. And this problem is also fixable, but we need to do some more learning. Specifically, we need to learn about something called skyQuery. So skyQuery is one of those other query implementations. So the generic query implementation of Bazel works by kind of using Bazel's build file parser and loader to load all the targets, and then it copies all of those target graph information into a separate graph and does the query over that. So that makes it very flexible because it's a very generic graph implementation. But it also means there's this overhead involved in copying targets into the other graph. skyQuery, on the other hand, uses Bazel's native incrementality loading framework directly to implement query. And for that, we get slightly different performance characteristics. So there's less copying, and it might be a little more performant, especially with really large universal queries like what we're doing here. But we also get a slightly different feature set with skyQuery. In particular, we can't ask for our output to be ordered in any particular way. So to activate skyQuery, we have to pass -- order output equals no. And so that's OK for the selected target, the target selection case, because we don't really care what order we get it in. We just want all of the targets. And then we also have to use a option called -- universe scope. And that's going to be the total universe that we're allowed to access within the query. So we're going to be passing // in there. Anyway, the main advantage we get from getting skyQuery, at least in this case, is that we get another function called rbuildfiles. And rbuildfiles takes a path, for example, a starlark file, and tells us all the build files that transitively depend on that path. All right, so our first attempt to use this actually might fail like this. All right, so we're using our build files, and we're passing in our starlark file, but we're still getting empty results. Does this thing not work as advertised? Well, actually, if you go carefully read the documentation, you'll see that our build files, unlike every other Bazel query function, does not take targets. It takes path fragments. So we have to go pass a path, not a target. And if we do that, we'll finally find out that foo/build depends on that starlark file. Great. OK. So now that we've found all the build files that depend on a starlark file, we can apply the same logic where we get all the targets in those build files and then mark all the targets there and all their reverse dependencies as affected. Great, like we can go and we'll be using the siblings function, right? So that should still work. I won't show you the combined query. Let's look at the next problem. And at this point, I'm sorry to announce that my problem counter works like the Bazel action counter. And yes, we're up to 5 in the denominator. Who knows how high it will go? But anyway, problem three has to do with, well, what if instead of modifying a file, we deleted a file? All right, so if we ask for the reverse dependency of a deleted file, Bazel quite reasonably is going to tell us, I don't know about this, it doesn't exist. But removing a file could still modify the build graph. For example, if there was a glob somewhere that has stopped picking up this file. So we need to do something about this. And the something that we have to do is we have to go back to the old version where this deleted file exists, compute the affected targets of the deleted file, and then bring those forward into the new universe and intersect it with all the targets that exist in the new version. OK, so we're going to have to run at least 2 queries now. Let's jump on to problem 4. Which also has to do with adding or deleting files, but this time build files. And it revolves around a problem with the glob function. So the glob function, which lets you pick up lots of files in build files, can be used recursively. But it cannot cross package boundaries. So a recursive glob will pick up files and directories until it hits another build file, and then it will go no further. This means that if you add or remove a package, you can affect the globs of its parent packages. This is another problem where we have to figure out what the files which are affected by this are and kind of invalidate all the targets in those files. So this is particularly annoying because we can't really do it in the context of query. We kind of have to manually traverse the file system and find out packages which had sub-packages added or deleted. But this problem is fixable. And then eventually, we'll end up with something great like this. This is our universal reverse depth computing query. So you can see we have all of our fixes. We have the reverse steps of the change files. We deal with the build files. We deal with the starlark files. And then we deal with the build files with added or removed sub-packages. You'll see I have to filter out the paths by extension. And I did that by ensuring some horrible shell. That's because I don't have to maintain slides code. And then finally, we have another query which we had to run previously and insert into this one, which is the affected targets of deleted files from the older version. All right, so this plugs most of the holes. But we might have to. This is far cry from our original intention here, where it seems so nice and easy with our one RDEPS function and one test function. And if this actually works, we've certainly, our quest for elegance has certainly taken a cold shower. And since that's really what matters in software engineering, I don't want to do this. So let's take a step back and reconsider. All right. So thinking about this again, at the beginning, I said that a target is approximately, at the loading phase, a name with some attributes. And there's actually a way to get Bazel to tell you what the attributes are. So far, we've been using query in a mode where it only outputs the names of targets. But query is quite capable of telling us basically everything there is to know about a particular target. In particular, if we pass -- output equals proto, Bazel will emit a giant proto for all the targets which are the output of the rule. So here's an example from my foo package. So you can see there's a target message. It tells us what type it is. It's a rule. It tells us what its rule class is. And then each attribute has a protobuf, which tells us what its type is, its name, and its value. And then finally, at the end, we have some rule input attributes. And this tells us what rules this particular target depends on. So thinking about this a little, and also thinking about cryptography, we can go back and appropriate an old idea from cryptography. So old is important because that means the patent has expired. And that old idea is the Merkle tree. So what I want to do is take my target dependency graph and associate a hash to each node, such that the hash depends on the attributes of that target and also all of its transitive dependencies. And using that, I can tell whether a particular target has changed or not. So the way that works is that at the bottom of our dependency graph, we usually have a lot of source files. So for example, lib.cc. So we could just say that the hash of that node is the hash of the contents of the file. And then moving up a level, we have our lib rule, which actually contains the source file. And so the hash of that will be the hash of all of its attributes, for example, the cops, plus the hash of its source file, lib.cc. And finally, at the top, our test has its own attributes, and it depends on mylib. So we hash all those things and get a final hash. All right, so perhaps it's a little easier to see this in code. To hash a target, we just go through all of its attributes. We can just hash the attributes by reserializing the attribute protobuf or message, and then we recursively call hash target to hash all of the rule inputs. All right, so this simplifies a little because there's more things on the rule protobuf that we need, but it's largely the idea. And then using this information, we can write a little code to actually compute targets that are changed. So we're going to need as inputs all the targets in the old revision and all the targets in the new revision. So we compute a map from the target name to its hash for both the old revision and the new revision. And then for all of the targets in the new revision, first we check whether that target exists in the old revision or not. If it doesn't exist at all, then it's new, so we definitely need to run it. It's definitely affected, so we'll add that to our affected set. And then otherwise, if the hash of the target in the new revision differs from that in the old revision, we'll add it to our affected set. And kind of on a macro operational level, this is what this looks like. If we were using Git, so we check out the old revision, and then we run this query, which is pretty simple to sort of dump the entire Bazel dependency target graph as a proto. We save that. We check out the new revision. We run the same query, and that produces a giant proto file. And then we run our code, select targets, passing in the old graph and the new graph, and the files we think are changed. And then that runs the code up from the previous slide, which finally tells us that foo, my test, has been modified. OK, so on one hand, we've kind of given up on using query. We've sort of reduced Bazel to like a glorified incremental build file proto-dumper parser thing. And we had to write some code of our own, which is never good. But on the other hand, once you get your idea around the build Merkle tree, your head around the idea of the build Merkle tree, it's pretty conceptually easy to understand, and it's much easier to believe that this is correct rather than the monstrous query I was showing you before. But there's still another problem. And that has to do with external workspaces. And the root of this problem is that query cannot really tell you what files are affected in an external workspace. So like if I go look at an example, right? So if I have this HTTP archive file in or rule in my workspace file, then that defines a external repository at awesome third-party software. And if someone goes and modifies this URL, that will probably cause corresponding changes in the source files of the external workspace. But query just has no way to tell us that, to match up the change in the workspace file to that in the external repository. And partially, that's just because that's a truly impossible task. So this is a very tame external workspace, but it's very easy to have an external workspace that causes arbitrary code to execute, reads arbitrary things from the system, makes network calls, and is just basically flagrantly non-hermetic. And in that case, it's essentially impossible to compute the inputs to a workspace rule, or whether it changed or not, because the inputs are the world. So we can partially address this problem, at least for a restricted set of workspace rules, by using the disgusting hack. And so Bazel does not expose this information at all, but Bazel itself kind of has this problem where it needs to know whether to refetch a repository or not. And so it kind of stores a hash of what it thinks are the inputs to the repository in a special place in its internal output tree. So you also can go and slurp up these hashes, and then if they change, you know the repository changed. So it's gross but effective. So that plugs the external workspace rule. All right, with that behind us, I'd like to talk a little bit about the optimization of target selection. So this is a very critical piece of a continuous integration pipeline, selecting a test to run. For one, it runs on every single time someone wants to use the continuous integration system. And also, it's kind of in the critical path. It blocks actually executing the tests because we don't know what they are yet. And so we spent some time making this faster. And probably the most important thing we did was we made Bazel query into a service. So every time we were previously executing Bazel kind of like a shell command, we instead make an RPC. And the Bazel query service encapsulates the idea of checking out a revision of a particular revision of our version control system, executing a query, and then uploading the results to a persistent storage so that the client can actually access those results. So we have to use a kind of large file storage thing because these outputs can be in the hundreds of megabytes easily. All right, so why is this better? Well, one reason is that the Bazel query service can kind of maintain a farm of hot Bazel servers. And so that means Bazel's incrementality logic can avoid doing unnecessary work. It kind of has hot state of files that it's parsed, and also the JVM stays warm. Another advantage is that we can cache queries. So if you get the same request for a query on the same revision twice, you should be able to only compute that once. And then probably the biggest advantage is that we can execute queries in parallel. So you saw we have to have two queries. We have to have a query on the old revision and a query on a new revision. With a query service, we can just submit two queries at the same time and kind of get the results back in about half the time, which is a very major improvement because query is kind of the slowest part of this operation. All right, so you might reasonably wonder what it's like to operate the Bazel query service. It's kind of a weird service where it's I would say quasi-stateful. So the entire point of it is to have some maintained state, warm Bazel servers and caches and so forth. But also, if the cluster management software comes along and says this machine needs to go away, it's not too much of a loss to remove that Bazel query system because it's all re-replicatable by starting up new Bazels on the workspace. But another special property of Bazel query service is that because queries execute for so long, like minutes is not an unheard of time period, we need to have a special kind of front end for the Bazel query service that takes care of keeping track of which workers are busy executing queries and routes queries to the correct backend, which is free. And so Bazel is actually not too difficult to manage in this situation we've found, and kind of the most difficult thing actually has been Git. So Git it seems like if you execute it too many times on a repository or gets uncleanly shut down at some point, it just gives up and corrupts your repo or something. And so kind of a lot of the work of the stability, making the system stable has been just like parsing Git error messages to decide whether it's like completely broken or not, and we need to blow away the repo. And so that's one of the more disappointing learnings from this whole affair. Like, I'm not sure if this is because Git is just wrong or because it's just impossible to write data-preserving systems on Linux file systems. But either way, we can blame the same person, right? So, OK. Finally, I would like to touch on what I'm calling being incorrect for profit. And this revolves around the fact that only running affected tests only gets you so far. For one thing, it's very much depends on the structure of your dependency graph, right? So if you have many fine dependencies, you're much more likely to select out a lot of tests. If, for example, you have one giant monolithic web app where everything is an integration test that depends on everything, hypothetically, you might not win quite as much. But even with only running affected tests, it kind of seems like you only cut out of like say on average a constant factor of the number of tests you're going to run. And there seems to be a sad fact that test execution time in CI systems grows quadratically. And the two quadratic factors are the number of changes and the amount of code. And like quadratic growth is, no one wants to wait for quadratic growth for their tests to run. And most importantly, companies don't want to pay for quadratic growth in testing resources. So this is not really an acceptable situation to be in. So we need to apply some even more aggressive strategies to prune the tests that we're running. And there's several ways of going about this. One is batching. So that's where you take a whole bunch of test changes, and then you compute the affected test set over all of them and run the test once. So that way, you only run a test at least once for all these changes. It does have the complexity that it kind of extends the tail of getting test results for changes in the middle. It also means you want to have some sort of automatic bisection system to find out if tests were broken in between. But it can dramatically reduce the number of test executions, which are largely duplicate that you have to do. You can also apply policies which bound selection. So you can say things like, well, we're only going to run tests which are 4 hops in the dependency graph away from a file that was changed. And the goal here is to hopefully tests which are closer to the code being changed are more likely to actually find problems with it. And finally, if you want to be really clever, and modern, you can do predictive testing, where you try to guess what tests are most likely to fail. So usually do this with statistics or other kinds of machine learning. Google and Facebook have published some interesting papers about this. All right, so with that in the bag, I'm largely done. Here's an image credit for my first slide. And I'll turn it over to you if you have any questions. This, of course, is my email address. You can reach me there until such a time that one entity on either side of the @ sign decides to call it quits. Please do check out our other talks and our open source Bazel tools on GitHub. Thanks.
Right, so talking about hidden gems, I think Benjamin talk is a hidden gem on every BazelCon so far. So, and I'm also looking forward to an actual talk about hidden gems in Bazel Codebase. And with that, are there any questions?
Hi, yeah, Itai. I have 2 questions. One is, what's the order of magnitude? Like, how much time does this take? How much time does a commit need to wait? A build request needs to wait?
So I think this is completely proportional to the size of your workspace. So I think we're at about 2 minutes to do this selection. Is that right? Yeah, 2 minutes.
And did you consider preemptively running the Bazel query, based on basically get events, so that when the build request comes, then maybe you've already computed the Bazel query?
Well, it's not really preemptive because our CI system is triggered off Git pushes.
Oh, okay.
So there's like, there's not
no
really any
gain there.
guessing to be done in our case anyway.
Okay, and actually a third question, did you consider having basically an in-memory the graph instead of running Bazel query?
So I mean, well, you would still need some way to update that, right? And you need Bazel because Bazel is the only thing that's capable of doing the like somewhat complex work of parsing build files and like turning that into targets, right? So Bazel is the one that has the in-memory graph, and probably if we wanted to be clever, we would actually just like hack up the Bazel code base to do this selection incrementally for us. Like that would be the next performance frontier, because there's this whole point like, why are we like serializing this into protobuf so we can put it in memory in another program and like hash it? Like something is a little silly here. That's another scaling boundary, I think, which we'll eventually.
Because rumor has it that at least some companies have in-memory graphs of a Bazel graph, and one can think that maybe the community would also benefit from having.
I see. You're like me this morning. Yeah. I can't help you with Google. Sorry.
I'm Tran from Neuro, and I have two questions. First is that if we change the action of some rule, which is like from input by BZL file, would that be captured by a hash?
An input?
Not input, like the action. Like I can change the BZL file and say what's the action execution rule.
Well, so the Starlark file, yes.
Yeah.
So that's actually a good question, which was something I elided for simplicity, which is that Bazel sticks an extra magical attribute on every target, which is called the rule implementation hash, which is a hash of all the code that goes into computing that rule. So if you just stick that attribute into your overall target hash, then that takes care of that.
Oh, great. And the second question is it like the hashing or like all the tool, like is there any open source?
So it's ours is not open source at the moment. It doesn't have too many dependencies. We can think about it.
All right, thank you.
Tradition.
Hey, I both. I work for Google. I was wondering if you're using the right query options, because the ones on the slides were not the right query options.
I also elided some stuff for. That's not exactly what we're running, but what are the right query options?
I did a little bit of work on query performance earlier this year.
You know what's funny? If you advance my slide by one and show it. It'll probably be about what Ulf is going to tell us about, but maybe he's better. Graphless query?
There is graphless query.
Something else?
Yes.
What is that?
Well, you should also use auto output equals no in all cases.
Yeah, I know.
And the third is stream proto.
Yes. I meant to start using that, but I didn't.
Excellent.
Thank you. That's a good point, though.
Yeah, so just for everyone else here, graphless query avoids making a copy. That's what it says here. And the advantage of using stream proto is that it doesn't construct a single giant proto in memory, right? You get a problem when you get to like 2 GB protos, because then the int isn't large enough to address the entire proto. And then it'll fail with an out-of-memory error because it can't allocate an array that's large enough. Anyway, thanks.
The stream proto is a very, very good hint.
It's obvious that at least the documentation and definitely the set of flags we have needs some improvement here. So that's obvious. Of course, yeah.
Hello, I'm John from Stripe. 2 questions. First, would it be correct to say that this is a mitigation for lack of remote test execution?
No, because as I was trying to say this at the beginning, but if we never want to run Bazel tests // ... because that already does a huge amount of work on every target in the so basically like all the work up to actually executing it. And so like we want to be able to eliminate tests like at the many levels, but like sort of the level where we have to do the least amount of work on it. And so we don't want to analyze all rules. We want to be able to prove that they can't be affected sort of as quickly and is with the least amount of resources as possible.
And another strategy I've seen used with some success is having sort of metadata files at different levels of the source file system, where you say anything under this directory needs to run these tests, and then if you make changes outside of that directory, you may not necessarily need to add that test to your test set.
Well, that sounds like a workaround for something else.
Okay. I'll let him answer that comment.
Right. Thanks, Benjamin.